Next we talk about acceleration. Acceleration of a moving body. Acceleration of a body gives us an idea as to how the body is changing its velocity. If a body continues to move with same velocity throughout, then we say that it has no acceleration. It's moving with a uniform velocity, which is also called uniform motion. But in case the velocity of a body changes, we say that the body is under acceleration. So acceleration essentially measures the rate at which the velocity of a body changes. So by definition, acceleration, which is denoted by A and it is a vector quantity, by definition it is the rate of change of velocity of a body. Rate of change of velocity, which means that let us say there is a body which is moving with a velocity v1 at a given time t1, and after some time when the body has reached somewhere after travelling, it is found that the new velocity of the body is v2 at a given time t2. Then we can understand that in a time interval of t1 to t2, the time interval itself will be t2 minus t1, right? In this time interval t2 minus t1, the velocity of the body has undergone a change from v1 to v2. So, the change in velocity will be v2 minus v1. The final velocity minus initial velocity will give us the change in velocity, and then by definition the acceleration of the body would be the change in velocity delta v by the time interval in which this change is brought. So, this will be v2 minus v1, the change in velocity by the time interval t2 minus t1. So, this is how we basically define acceleration, but here also understand that there can be various ways depending upon how large or how small this time interval delta t is. We can define what we call as average acceleration first. Average acceleration, which would be the acceleration of a body over a big time interval, the overall acceleration by definition would be the total change in velocity by the total time taken in bringing that change, right? So, where the time interval delta t will be a large time interval, right? So, this definition that we have written here essentially will be valid for average acceleration also if t2 minus t1 is a big time interval, right? So, if this time interval is big. So, in this case then the same definition will work for average acceleration also. See that the direction of average acceleration will be the same as the direction of change of velocity. This is important to take care of. The next acceleration that we talk about, as we have studied about speed and velocity, it is the instantaneous acceleration, which, as we understand now the term instantaneous, it is the acceleration of a body at an instant, which means the rate of change of velocity at a given instant of time. So, we can just write it as a with a subscript instant or simply a. When we write simply a, that means we are talking about instantaneous acceleration itself. Now, how do we find out instantaneous acceleration? In the same definition, we have to bring down our time interval delta t to a very small value, such a small value so that it approaches 0. So, what we do here is we put a limit on delta t that it approaches 0, and then we find out the rate of change of velocity delta v by delta t. When we do that, we know that if the time interval delta t becomes very small, it is written as dt, and the corresponding change in velocity in the same time interval will be written as dv, a very small change in velocity divided by a very small time interval, which we can call as an instant of time. So, this becomes the definition of instantaneous acceleration, dv by dt. This is an important relation. It is through this relation that we derive many other relations when we talk about different types of motions of bodies. This, as you can see, is nothing but the differentiation of v with respect to t. Differentiation of velocity with respect to time, right? We also understand that by the formula itself, a is equal to dv by dt, we understand that dv by dt is nothing but the slope of the velocity time graph, vt graph, as we have discussed in case of speed and velocity earlier in the previous videos, we understand that if we have a VT graph, the velocity time graph with us, the slope of that graph at a given point will give us the acceleration of the body. So, slope of VT graph gives the acceleration, the instantaneous acceleration, right. So, this is one observation that we make from this particular expression. Also, we can slightly change this expression to write it as dv, the small change in velocity, is equal to a dt, the product of acceleration at that time, times the small interval of time dt. This expression gives us a very small change in velocity dv that a body will undergo in a small time interval dt with an acceleration a. So that if we just add all the small changes in velocity, we will get the total change in the velocity of the body. So, how do we add small changes? We integrate dv. As we integrate dv, we will get the total change in velocity, which we can call as delta v, the total change. And on the right hand side, this will be nothing but integral of a dt. But once again, do we know that integral of a function with respect to a variable gives us graphically the area under the graph of that function? Can we say integral of a dt is nothing but the area under the at graph, acceleration versus time graph? So, another result that we get from the same expression is that area under the acceleration time graph gives us the change in velocity of the body, gives change in velocity. This is also an important expression and a result to know. You can directly use it into graphs to get various answers. So, one is that the slope of velocity time graph gives us acceleration, and the second is that the area under the acceleration time graph gives change in velocity. Okay, we shall be using these when we study motion through graphs. One more thing that we can observe here is the SI unit. The SI unit of acceleration, the way acceleration is defined, it is change in velocity by the time interval in which the change is brought. We can say that the unit of acceleration will be the unit of velocity, which is meter per second, divided by the unit of time, which is another second. So, you will have meter per second. So, it will be meter per second squared, which becomes the SI unit of acceleration.